everybody. In this video, we're going to spend a few minutes talking about why there's a difference between heat capacity at constant pressure and heat capacity at constant volume. We can figure out what's going on based solely on this equation. The equation just says that the change in the internal energy for a substance is equal to the heat added plus the work done on or by the substance. Let's start with the constant volume case. What does the change in internal energy consist of? Well, we know that the change of internal energy is just equal to the change in thermal energy plus the change in bond energy. But we're talking about a gas here, and it's always going to be a gas, so there is no change in bond energy, and delta U can just be rewritten as the change in thermal energy. What about Q? Well, Q is just the energy we add to the system, however much it is. And lastly, what about W? Well, we said that we're doing this as a constant volume process. How much work is done during a constant volume process? The answer is just 0. No work is done during a constant volume process. So our equation is complete. Delta E thermal is equal to Q. In other words, all the energy that we add to the system will go directly into changing the thermal energy of the particles. In other words, warming them up. But what happens if we do the same thing at constant pressure? Well, these first two terms are the same. The change in the internal energy of the system is just a change in thermal energy, and we're adding energy in the form of heat. But now, work is no longer 0. In order to keep the gas at a constant pressure, we have to allow its volume to change. What is the sign of W going to be? The other equation we need to figure this out is the ideal gas law. Let's use this to figure out what happens when we're dealing with the constant pressure case. If pressure is constant, but temperature is increasing, what does the ideal gas law say about the volume? We're assuming that the number of particles is remaining constant for our problem, and R is also a constant. So if T is increasing, but P is staying the same, then V must be increasing as well. But if V is increasing, then is work positive or negative? Well, this equation says that if the change in V is positive, then work is negative. So if we add energy to the system, not all of it actually gets to go into the thermal energy. Some of it is lost in the form of work. This means we have to add more energy to this system in order to heat it up the same amount that we did the constant volume system. The reason, again, is that in the constant volume system, all of the energy that we added went into heating up the gas. In other words, increasing its thermal energy. But with the constant pressure system, this is not the case. The gas is both warming up and expanding. In other words, doing work on its surroundings. So that energy we added is being split. We can actually use this information to determine what the relationship is between heat capacity at constant pressure and heat capacity at constant volume. Let's use these equations to calculate the heat capacity at constant pressure as it relates to the heat capacity at constant volume. Let's think about what heat capacity is. Heat capacity describes how much energy we have to add to the system in order to increase its temperature. When we were dealing with heat capacity at constant volume, in other words, when work was 0, the change in the thermal energy divided by the temperature was equal to the heat added divided by the temperature. This made it easy to calculate the heat capacity. But now we have to consider work. However, heat capacity is still defined the same way. It's the amount of energy we add divided by the change in temperature. This variable Q represents the amount of energy that we're adding. So if we want to find the heat capacity at constant pressure, we need to rearrange this equation so that Q is by itself and then divide by T. This is our definition of heat capacity. The key point to remember here is that the energy that we're adding to the system in the form of heat is being split into two different pieces. Some of it is going to increase the temperature and thermal energy of the substance, but some of it is going into work. Let's start by thinking about this term. What is the change in thermal energy divided by the change in temperature? Well, we know that it's equal to the heat capacity at constant volume. For the heat capacity at constant volume, we had this equation. But we see this piece right here. Again, if no work was being done, then the heat capacity would just be equal to the heat capacity at constant volume. But there is work being done, so now we need to evaluate what this piece is. But first, let's rewrite this as the heat capacity at constant volume. What is work in general? Well, for a constant pressure process, we know that the work done is equal to the negative pressure times the change in volume. So let's just replace work with negative pressure times the change in volume. Note that the negative in the definition of work and the negative sign right here will cancel out to make a positive. But what is this number here? P delta V divided by delta T. Well, to find that, we need to use the ideal gas law one more time. The ideal gas law says this. In this example, we're assuming that pressure, N and R, are constant, while V and T are changing. So if this is the case, then what is P times the change in volume? Well, it's just equal to N times R times the change in temperature. We want to know what this number is. So all we need to do to get this is divide both sides by delta T. And there we go. This number is just equal to NR. So let's replace this with this. And there we go. We found our expression for heat capacity at constant pressure. It's related to heat capacity at constant volume. But as we expect, it's greater than heat capacity at constant volume because the energy that we add to the system is not allowed to all go into actually warming the system up. Some of it has to be expended in order to make the system larger. Now let's take a moment to talk about a new concept in this DL, enthalpy. Enthalpy is a new state function in thermodynamics. But you might be asking, why do we need another state function? We already have plenty of them. Internal energy, pressure, temperature, all these things. Using enthalpy as a state function is useful because it has a nice relationship to heat. In a system where pressure is constant, then the change in enthalpy will always be equal to the heat added or removed from the system. Heat is a process function, but enthalpy is a state function. So we've effectively turned heat from a process function into a state function. If we can evaluate the enthalpy of a system at a particular state, and then evaluate the enthalpy at another state, we can calculate directly how much heat we had to add to the system in order to take it from one state to the other. It's just equal to the change in that enthalpy. As with other state functions, we like to draw graphs with enthalpy. One common one is a enthalpy temperature diagram. You drew one of these in your DL today when you were doing the activity about sweat. As with other graphs of state function, we represent particular states that we're interested in by points. This point represents a specific enthalpy and a specific temperature. This point represents a different enthalpy and a different temperature. We move from one state to another state through a process, which is represented by a line. We've drawn several of these graphs already, so I'm not going to spend a ton of time talking about how these work. But the key thing I want you to remember here is the relationship between enthalpy and heat. If you're dealing with a process that is at constant pressure, then the change in enthalpy will always be equal to the heat added or removed from the system. One of the reasons this is so useful is that many chemical reactions take place at a constant pressure. We're not going to do a ton with enthalpy right now, but we're going to see enthalpy again later in this course in the context of chemical reactions. Next DL, we're going to look at something that's very closely related to thermodynamics. We're going to have to do some statistics, but don't worry, we'll help you through it.